Hello, everybody. It's my pleasure to chair the third distinguished seminar of the year. Today we have Professor Sarah Haigh from University of Manchester, and I'm Salvador Eslava, a senior lecturer here and EPSRC fellow. And Sarah is a professor of materials characterization at the University of Manchester. Her research interests center on improving our understanding of nanomaterials structure and properties using transmission electron microscope, imaging, and analysis techniques. She has a particular interest in advanced TM characterization of functional two-dimensional materials and vertical stacked heterostructures and in developing in situ TM imaging methods. She sits in many different committees and of companies and societies, including the BP at ICAM, where she is the director. She has won many medals, such as the Rosenheim Medal, the IOM3 Silver Medal, and the RMS Innovation Award, in recognition of her distinguished achievement in material science. She has published 200 articles, including 40 as corresponding author and 5 book chapters. She has more than 13,000 citations. The presentation is going to be 45 minutes, followed by 15 minutes of questions. You can write down, for the people online, you can write it on Teams or Zoom, whatever we are using. and the people here in person, you can ask the questions here. Okay? And yeah, so that's all. The title of her presentation is Atomic Resolution STM Imaging in Liquid Environments. Thank you very much. The floor is yours.
Thank you very much. Thank you very much indeed. It's a huge privilege to be here and to be here in person. It's so much more fun lecturing in real life than it is lecturing online. But it's wonderful also to have the online audience and to be able to attend in locations where you otherwise wouldn't be able to engage with science. So I think this hybrid format is actually really perfect. So I'm going to tell you today about how we can observe single atoms in liquid, and I believe that this is the first time that people have really been able to watch atoms move on a surface surrounded by a liquid environment. I'd like to thank my research group for doing a huge amount of work towards this goal over the last 5 or more years. On this introductory slide, I've separated them into black, who are the microscopists, those in blue, who are the ones that make the samples that we are looking at, and those in purple are the theorists that provide that fundamental understanding to help us interpret our results. So my talk is about scanning transmission electron microscopy, and I wasn't sure about how broad the audience was going to be. So I thought we better just check that we're all on the same page by explaining what a scanning transmission electron microscope is. So this is a picture of one of the ones that we have in Manchester. It's called the Titan. And what we have is an electron gun which fires electrons through a very thin sample. And that sample being really thin is going to come up as being important later on. We then have some lenses, and we can collect lots of different signals that have come off of the interaction of the electron beam with that specimen. So we can detect the directly transmitted beam, and we call that a bright field image. We can look at the scattered electrons. We call that a dark field image. We can look at the X-rays that have been generated by the interaction of the electron with the sample, and that's energy dispersive X-ray spectroscopy. We can look at the energy that the electrons have lost as they pass through the sample, and that's electron energy loss spectroscopy. And the picture on the right-hand side here just shows you some examples of the types of information that you can get about different types of samples. So the top are some quantum dot nanoparticles. These are cadmium telluride, cadmium selenide. And so you can see in the elemental mapping that there is a core shell structure. This one is a lead structure, which we didn't know would phase segregate into lead selenide and lead sulfide, which is the funny cubey things. We can look at, in this case, this is a monolayer. The middle image is a monolayer of a tungsten doped molybdenum disulfide, and the high angle annular dark field imaging mode, which is going to be an awful lot of the data that I'm presenting you, is from this high angle annular dark field imaging mode. And the reason that microscopists really like high angle annular dark field, or HADF, is because it's more directly interpretable than lots of the other imaging modes. So in this picture, I can tell you that the brighter atoms have a higher atomic number, so-called Z contrast. So that means that the bright atoms are the tungsten, and the lighter atoms that you can see in that nanometer sized flake of tungsten molybdenum disulfide are the molybdenum atoms. The sulfur atoms are even lighter. You can hardly see those on that image. At the bottom, there's another example, which is an elemental map taken using electron energy loss spectroscopy. And it's actually possible to get atomic resolution elemental maps in both EELS and EDS. The caveat to that is that your sample has to be really, really stable under the electron beam. So it has to take millions of electrons per square nanometer in order to be able to get these atomically resolved elemental maps. And the stability of the sample comes up a lot in electron microscopy discussions, and it's something we need to think about as we're doing our experiments. And I'll talk more about that later. So generally what we get when we do electron microscopy is a two-dimensional image of a sample. I'm not going to focus on three-dimensional imaging. I just wanted to mention that we also can do three-dimensional imaging by taking lots of two-dimensional images and combining them a bit like they do in an X-ray CT scan in order to get a three-dimensional elemental map. And if we do that with an X-ray map to the X-rays that have been generated, that EDX mapping, you can then create an elemental map in 3D. But whereas X-ray maps tend to be at the tens or hundreds of nanometer scale resolution, the elemental maps that you can get using scanning transmission electron microscopy tomography can be right down to the atomic scale. Okay, so that's kind of an advert for a different talk. So what am I going to talk about? So in this talk, I'm first of all going to give you an example of some recent work which we did looking at a reaction that happens in liquid. And we've done this, the whole of this experiment, we've done ex situ. So taking samples that had been in liquid, drying them out, putting them in the microscope. I'm going to show you that because it demonstrates why we would really like to be doing this experiment in liquid in the microscope. The second part of the talk here, I'm going to tell you about why it's difficult to do an experiment in liquid in an electron microscope. And then I'll tell you about some of the recent developments that we've done, allowing us to perform liquid-liquid mixing reactions. And as I said at the beginning, tracking single atoms moving around in a liquid environment on a solid surface. So this is that motivation for a liquid phase experiment. Now, I didn't know what the audience would be all aware of this, so I'm going to start by introducing the materials that we're studying. So these are clays and micas. Clays and micas are two-dimensional materials, but you're probably more familiar with them as something that you would find on a walk in the countryside, up a mountain, in your garden. So they're a big component of soils. And they are the flaky minerals that you might find in your garden. And they're flaky because they're composed of these aluminosilicate planes. So planes of aluminium, silicon and oxygen layers, which are shown here in these blue lines. And those planes of atomic structures are sandwiched together with cations. And the cations can be a wide variety of different species. And a key feature of these cations is that they're readily exchangeable. So the native cations could be something like potassium or calcium, sodium, and you can exchange them with different ions that happen to be present in the environment. Now that's really important because if you have a nuclear disaster and there are radioactive cations have been leached out and been present and ended up in the soil, then these clays and micas will adsorb, take up the cations in those interlayer spaces, and that radiation will stay in the soil for a very long period of time. If it isn't taken up by the soil, it'll end up in the water and it'll flow out through the environment. And that was the scientific question that I was introduced to when I first started looking at these materials with Sam Shaw back in 2005 or so. And there they had been doing experiments with cesium ions. We can use a non-radioactive isotope of cesium to understand the behavior of the radioactive cesium, which is a problem from a nuclear disaster. And they wanted to know how these clays and micas, different minerals, we particularly focused on illite in those experiments, how illite was taking up these clays in order to be able to understand the mechanism and therefore predict how much soil you have to remove, how much radioactive ions are going to end up in the water, these types of things. More recently, I've been working with colleagues in Manchester, Marcelo Lizardo Hidalgo, who has been very interested in the technological use of clays and micas. So they are used in things like proton exchange membranes as part of the membrane materials. They're used very widely for water filtration, so filtering out unwanted ions from drinking water to purify drinking water, to produce pure drinking water from salty water. So what Marcelo had discovered was that if you make these clay materials or mica materials very thin. So rather than a bulk material, which would have tens, hundreds of thousands of layers of aluminosilicate atoms, what Marcelo has discovered was that the performance of the materials in the membranes was improved by orders of magnitude if you made the materials atomically thin, just a few layers thick. And that can be done very readily using the same type of approaches that people use for chemical exfoliation of graphene. Yeah, you have graphene, your graphite, you put it into a solution and you can persuade it to chemically exfoliate so that you have few layer graphene flakes. We can apply that same technology to clays and micas, but now you have this possibility to tune the behavior of those materials by changing those interlayer cations using a solution. Okay, so we started wanting to look at understanding cation exchange within few layer clays and micas. Now, as I said, there is still an awful lot of controversy in the community about ion exchange in bulk materials, but really nobody has started to look at ion exchange in few layer crystals. The structure that you can see here is a 2-layer aluminosilicate structure, so 2 layers of vermiculite, and these ones here I'm showing you are the aluminosilicate layers, and we've exchanged it with cesium, and we've exchanged it with cesium because cesium is bright and we can see it easily in the electron microscope, as well as the fact that it is relevant for this radioactive waste contamination. So we can see that layer of ion exchanged cations, cesium cations. In order to be able to prepare this and put it into a transmission electron microscope, I've taken that bilayer specimen, which is on a silicon oxide substrate, and that's shown underneath here. We've encapsulated with a graphite layer just to protect it, and then we've used a focused ion beam to slice through it, pick up that slice in cross section and put it into the transmission electron microscope. The alternative approach, we can look along a different direction and we can look in plan view. So looking down on the plane like you would expect to look at graphene, for example. And now you can just see that layer of intercalated cations. And you can see that they're arranged in this beautiful hexagonal pattern as you'd expect from the schematic picture above. So this is just 2 layers thick. If we have 3 layers of vermiculite, now we have 2 layers of intercalating cations, and we end up in plan view with these 2 layers are superimposed, but with a small offset. And that's what gives you these lines in the pictures that you can see here. These lines are the offset of those 2 hexagons. And in plan view, again, you can see that those 2 lines are offset, and we can see the 2 individual layers of cations. For anyone who does microscopy in the audience, these materials are pretty beam sensitive, and so you tend to get one shot at these types of pictures. So we wanted to understand whether ion exchange was happening differently in few layer crystallites as opposed to in many layer bulk materials. And so this involved more than 60 different samples, looking at the effective thickness, looking at different amounts of time that the clay, in this case just vermiculite, had been in the solution with the cesium cations. And this is a summary of those over 60 different VIB specimens and analysis in the microscope, and that's what's shown here. And hopefully you can see that if you plot the number of layers along the bottom here, that's the number of aluminosilicates in your structure. If you only have one aluminosilicate layer, then there's no interlayer. So this is just interlayer exchange. And you can see that this increases to log scale by 5 orders of magnitude when the thickness of your sample is just by layer. And so we were very excited by this. We thought this is one of the reasons why these materials might be able to behave so much more quickly, because the diffusion of cations into this interlayer space is happening 5 orders of magnitude more quickly. So this is a sample here of that 2-layer vermiculite. You can see that single bright line of atoms that traverses over tens of micrometers. And when you zoom in, you can really see it is single atoms. In the bulk structure, which in this case is just 33 layers, but we've looked at thicker samples as well, you can see that interlayer exchange is more heterogeneous. And that's reflected by this, the different levels of brightness across the different layers. Okay, so we understand that this is giving us the potential for maybe producing membranes that will operate orders of magnitude more quickly. So we went to Rahul Nair's group and said, well, can you make us some real membrane so we can test this? You know, reviewers are going to be more convinced than if we just show them electron microscopy. We can show them a real thing. So this is the membrane that was produced. It's so 10 millimeters or so across, and they have looked at much bigger membranes. And you can see that, yes, indeed, the ion exchange, so the rate at which they take up cesium is a few hours as opposed to 14 days on when you are using a material made out of bulk powder. So you still crush the powder, it's just that the powder of vermiculite is then composed into a membrane as opposed to exfoliating it using few layer flakes, creating the same membrane and measuring it. You get this, again, orders of magnitude improvement in the rate of ion exchange. So the referees said why? And we thought that was a good question. We should have thought about that earlier. And so we decided to, we were suggested to do some atomic force microscopy. And so we went into the lab and did some atomic force microscopy in liquids. And even that is actually pretty challenging. So we looked at atomic force microscopy of the two-dimensional flakes in liquids. We had to anchor them really well to the substrate. Otherwise, you put the liquid in and they float off. So we anchored them onto the substrate, having developed this technique. And you can see that the monolayer, so no interlayer, just one aluminosilicate layer flake, does not change its height. Whereas the two layers changes its height by 5 nanometers, even though it is still stuck to the substrate. The 3-layer flakes increase by a bit less, 4 nanometers. The 4 layers here increase by 2 nanometers, 5 layers a bit less, a bit less, a bit less. So that is telling us that in the bilayer flake, the separate between the bottom aluminosilicate layer and the top aluminosilicate layer, that space has increased by around 5 nanometers. And that is the reason for the fast diffusion. When the flakes are atomically thin, the layers themselves can separate to a dimension which allows that hydrated cesium ion to be able to penetrate into that gap. And that effect is decreased, and we've done some density functional theory calculations to be able to understand the difference in the interaction and what happens when you start taking layers away from the structure. And that's supported by this strength of interaction, that the interaction between the layers is much greater. And this behavior then tends towards the bulk when you're getting up to 7, 8 layers. But when you have membranes made out of the very few layer samples, and if you look at what the distribution of atomically thin plates within our layers was, shown in this on the right here, you can see that the majority of these exfoliated sheets were just 1 layer thick. And that means they didn't have an interlayer. So more than half of the flakes in our membranes don't have an interlayer. So they're really not contributing to this interlayer expansion. So that means that there's even more that could be done if we could optimize these materials to have 2 to 3 layers as opposed to mostly 1, and then 30% 2 and 15% 3. So there's a lot more to be done. We've done a lot of work looking at clays and micas. This is a different mineral here called biotite. And one of the special things about two-dimensional materials is that they are almost entirely surface. And I said just now that most of the materials in our membranes are 1 layer thick, so they have no interlayer. But that means that they have an awful lot of spaces where they are stuck together. And that's a big problem with two-dimensional materials in the literature. You exfoliate them and then they stick back together in some random fashion. So that is called a twisted interlayer, because they are very unlikely to stack with exactly the right orientation so all the atoms line up. It's much more likely that they will restack with a twist angle, a little bit like if you throw paper on the floor, they all sit on top of each other, but the papers tend to be at different angles. And what we discovered was that the ion exchange happens preferentially within that twisted angle. So if you have 2 sheets of biotite and they fall on the floor and they have a twisted angle, then the ion exchange happens at that interlayer where it would never happen in the perfect crystal interlayer space. So again, this is chosen to be biotite because biotite does not ion exchange with cesium in hundreds of years. And so we did this experiment with a twisted interlayer space, which is what's shown here. And what happens is that you create these beautiful islands of cesium atoms just at that interlayer space. And this is really intriguing. Understanding why you might get cesium ions, again, we work with the theorists to be able to look at these potential wells. And it turns out you get these well potentials where it's more favourable to exchange for cesium, and so the cesium ions fill up these potential wells, which are produced by the twist angle of your moire lattice. So you can kind of see the moire lattice. It varies in the dimensions. It's a superlattice produced by the overlapping of two twisted lattices. Okay, and we think that's got loads of exciting potential in things like quantum computing, trying to understand how you could tune those islands to produce special arrays. So the other feature isn't just these interlayer spaces, you also have surfaces in two-dimensional materials. Yeah, and the surfaces can also ion exchange. It's just that the ions don't want to stay on the surfaces, so they're even more difficult to study ion exchange on surfaces. And this shows you a cross-sectional image. This is muscovite, slightly different clay, and you can see that we have 3 layers of aluminosilicate. We have the native potassium ions. They haven't been exchanged, so they're not very bright. We have cesium down at the bottom here, and we also have the potassium at the top. So this is our demonstration that we have ion exchange now on only the bottom and not on the top. We wanted to see if we could really study single atoms on the surface, and if we then go into plan view imaging, we can combine this dark field imaging with using scattered electrons with bright field image, which shows the lattice, and we can now start to be able to see single atoms on surfaces. And we observed that the exchanged atoms on the surface, cations on the surface, are sitting in a slightly different atomic lattice position than the original native cation, because the exchanged cation is hydrated, whereas the native cation, potassium, is unhydrated. Okay, so this took, the experiments we've told you about here took 3 or 4 years work. They took hundreds of samples. We had to look at lots of different conditions as a function of the solution concentration, as a function of the cation time, so the time that the material was exposed, as a function of the thickness. And we still don't understand the effect of dislocations, the effect of stacking faults, the effect of how those ions get onto the surface, how do they penetrate into the interlayer. There's a huge amount of more information which we could get if we could actually see what was going on. Okay, and so we believe that if you could do these experiments in the microscope and really watch what was happening, then you could massively decrease the amount of time it took you to study these types of solution phase reactions, but you could also vastly enhance the value of the electron microscopy to be able to study the differences between different regions of the sample, because that's what we're really interested in with electron microscopy. One of the great strengths of electron microscopy compared to bulk techniques like X-ray analysis is that we can actually look down at individual atoms and see what they're doing, as opposed to study an ensemble of thousands and thousands of atoms. Okay, so now we're going to move on to think about why we want to do experiments in liquid cells. And I'm going to use some analogies to wake us up a little bit. So back in the 18th century, people were drawing horses. Okay, and they were drawing horses galloping. And horses galloping were always drawn, doesn't matter whether you were in Russia or in France, horses were drawn with their front legs and their hind legs off the floor simultaneously, demonstrating how quickly they were moving across the ground. Okay, only in Russia the bears were driving the horses, which is great. However, it was only with the development of high-speed photography, so you could actually video how a horse gallops, was it discovered that there is no point when a horse is galloping when it is doing a kind of Superman impression. It just doesn't do that ever. If you look at the slows, there is no point where it doesn't have a foot on the floor, even when it is absolutely at full rate on a race course. And people didn't know that, you know, that is such a natural thing. People have been watching horses galloping for thousands of years, and they had never understood the mechanism of how a horse gallops. I have no idea. It's an excellent question. For those in the audience, the question is this true for all horses? If anyone can tell me and put it in the chat, that would be amazing. Okay, I'm also not an expert on prunes. So there is also a problem with the fact that the electron microscope requires a high vacuum environment. In order to prevent the electrons interacting with the air, which would also produce strong interactions. Electrons are great because they interact really strongly with atoms, but that also means it's challenging if you've got atoms that you didn't want to be looking at. So you need a vacuum environment inside the electron microscope. The problem is that when you put materials into a vacuum environment, and that includes anything that we think of as inert, like a gold nanoparticle. Put a gold nanoparticle into a vacuum, it's not the same gold nanoparticle as it was when it was in water or gas environment. The surface changes, the atoms rearrange themselves due to the presence of that vacuum. So we have to be careful that when we are analysing to discover what makes the best possible plum, and when we put it into the microscope, we come back and we tell the chemist who has created this plum that what they're looking at is they've developed this prune. Okay, because in order to be able to investigate it, we put it into the high vacuum of the electron microscope. But actually, what they're using it in is in a real hydrated environment, and it has a different, potentially a different surface structure. Okay. So I am not studying horses or plums. There are loads of different possible chemical reactions that you might want to be able to study that happen in a liquid environment. And these are just some of the ones. I've mentioned some work that we've done on ion exchange, which we've been really interested in. There's lots of work on electrochemistry, which we think is fascinating. Wet synthesis of nanostructures. An awful lot of the nanomaterials that we use are synthesized in liquids. There's physics. There's an awful lot of physics colleagues that I'm working with who are interested in understanding just the fundamentals of what happens to water at an interface. That is surprisingly poorly understood even at this stage of all the clever techniques that we've got available to us. In materials, corrosion is a huge issue, etching of material surfaces, and I'm going to try and avoid touching on biology. I think it's a really hugely important area, and we know that biological systems are almost entirely hydrated systems. They have additional challenges, and Alex is much better qualified to talk about electron microscopy of the biological systems. However, let's imagine that the chemical reaction that you want to do is represented by this fish tank, or more accurately, by the fish in the fish tank. So what you want to be studying is what happens to these fish when you throw food in the water, when you change the pH of that solution. What happens to the motion of the fish? What happens to the well-being of the fish, the growth of the fish, whatever it is. Now, if we stick with our vacuum phase electron microscopy, then the first thing we do is cause our fish sample to be compatible with a vacuum environment. And that will generally involve freezing it in the water really, really quickly and making it really thin. Those are my slightly unhappy frozen fish. Or slicing it up like sushi and having a look in a thin sample of fish, or freeze drying it. So removing all of the water and putting the fish in the microscope. Now, this is a hugely complicated and hugely important area of biological microscopy, and doing this for lots of different systems is a great art and something that's been developed over hundreds of years, I guess. But it's not the same as looking at a fish tank. Okay, we're quite a long way from that ideal experiment. And so, there's been a lot of work, particularly in the last decade, trying to bring that liquid environment into the electron microscope. And the way that you have to do that is to be able to sandwich your liquid in between two impermeable membranes so that the liquid doesn't escape and degrade the vacuum of your electron microscope. And this is the electron microscope we have in Manchester. It's very easy to use. You can see this is one of our smallest users. He's not very good. The electron microscope has a full range of in-situ holders. So we are equipped with holders that will allow us to put liquid samples, put gas samples into the electron microscope to allow us to do experiments in liquids and gases. So heating up the sample, mixing liquids, looking at the reaction products, etc. So they all work a little bit like this. We have a holder which has little pipes going through to the end to allow us to flow the liquid or the gas into the region where we're looking with the electron beam. Now, you can see that picture of the tip that's shown here on the left-hand side. The electron beam is just going to be investigating a tiny nanometer-sized region within the middle of that end of the TEM holder. The whole thing is about 30 centimeters long, and you push that into the high vacuum environment of the electron microscope. So if we take a cross section through that tip, the structure of the holder looks like this. So we have our liquid environment, which can flow in and out. We have two impermeable layers to protect the vacuum, which is here, from the liquid sample, which is there. And the electron beam has to be able to penetrate through both of those layers. The problem with that is that if you've ever asked anyone to do some electron microscopy for you, or indeed done electron microscopy, the general rule of thumb is that you want your sample to be tens of nanometers thick, ideally thinner. And electron microscopists get really excited about graphene because it's only 1 atom thick and it makes our life really easy. And even before you've put your sample into these liquid cell holders, you have 120 nanometers of liquid, you have 35 nanometers of silicon nitride to prevent the liquid getting into the vacuum, you have another 50 nanometers of liquid on the bottom, and that 120 nanometers is, with both fingers crossed, on a really good day. Quite often that thickness of liquid will be microns or even 5, 10 microns, you know, if you have filled your solution, your well, you might choose to have that thicker liquid, but in general, if you want to have high resolution, atomic resolution imaging, you need a thin sample. So even if your sample is a sheet of graphene or indeed a nanometer sized particle, you're putting it within a holder that has a total thickness of at least 200 nanometers. And that means that the resolution is much, much poorer than we've come to expect in the generation of aberration-corrected electron microscopy, where we're used to seeing atoms. Another problem with these types of holders is that the need to hold that liquid in place causes constraints for being able to detect other signals. It degrades the electron ND loss spectroscopy because of the presence of the multiple scattering in that liquid. But it also means that the X-rays are harder to get out and collect with the EDX detectors. Those EDX detectors are what tells us the elements that are present in our sample. And they're often blocked by the shape of the holder. You can see there. Okay, so this is one of the early papers showing liquid cell electron microscopy. It's not my work. It's a really nice example of what people are typically studying. So they were looking at the synthesis of these platinum ion particles, which then form into nanorods. And this is pretty representative of an awful lot of the electron microscopy liquid cell imaging that you get. So you can see nanoparticles moving around, and that is really exciting, but it's not being able to see atoms. And the reason you can't see atoms is because the liquid itself is too thick. So the second problem was this elemental mapping, and we were really fortunate to work with a guy called Nestor Zaluzek, who's a bit of a legend in electron microscopy and isn't afraid to pull bits off microscopes and break them and then stick them back on upside down. And so he took the holders that we were using and cut away pieces in this kind of butterfly shape in order to allow the X-rays to get out from the region that we were imaging the sample in. And so if you can see that, you know, schematic, it's now been commercialized, and so we have a pretty picture which shows how the tip of the liquid cell works. But by cutting out this butterfly pattern compared to the original liquid cell, you can now get the elemental mapping within these liquid cells. And that's an example of a complex nanostructure that's shown on the right. So you can now do this elemental mapping in liquids. But again, the resolution is tens of nanometers, same as the imaging resolution, about a nanometer. So a decade ago, there was a lot of excitement generated by this first paper by Yuk et al. Based in California, where they showed that if you take two sheets of graphene and brought them together in the presence of liquid, then you could create a water bubble that was protected by the graphene from the vacuum of the electron microscope. And because graphene is incredibly thin, you can choose a bubble with a dimension of 10 nanometers or so, tens of nanometers. You can have a thin liquid layer. You're only passing through 2 graphene sheets, and you can get these images which are shown here. Again, not my work, which show that you can get atomic resolution imaging in liquids, at least of these nanoparticles. And that was a decade ago. We think there's been about 10 more papers over the last decade. And if you're in the microscopy community, that's quite surprising, because this was hugely exciting. The idea of being able to do this imaging of nanoparticles in liquid really set people, oh, why didn't I think of that? I should go and do it straight away. And trust us, there were people all around the world, my group included, who tried. And the reason that we believe this is very difficult is understood if you've ever had some soup and tried to store it in cling film. So if you think about graphene, it's effectively an atomically thin sheet that sticks to everything, and it has a real tendency to crease, and you'll see that in the electron microscope images all the time. If you put a liquid sample onto one sheet of cling film, put another sheet of cling film or whatever type of a thin plastic you put on top of it, then the liquid leaks out. And the size of the pocket of liquid that you want is hard to control, let's say. So these liquid cells last a very short time, and it's really hard to find the right structure, the right size of liquid to get a bubble that is here. Sorry, that's 100 nanometers or so. Okay, so we thought, well, can we improve on this? And the reason that we thought we might be able to improve on this is because I moved in 2010 to the University of Manchester, where they have teams of people who are developing, making mostly electronic devices by stacking together graphene, hexagonal boron nitride, but also many, many other two-dimensional crystals. And they're at the point now where they can do that even in an ultra-high vacuum environment. We've been doing it in argon for some time. And so they can effectively create a designer electronic device by peeling with sellotape and different colored pencils representing the different crystals, peeling those off and sticking them back together. So this is the basis for creating a more engineered, a more controllable liquid cell. And the reason I say that is because if you combine a layer of your material which has a gap in it, as you can see here, and you can just etch that using electron beam lithography, then when you combine these structures together, you will end up with a gap within your heterostructure. And I'll show you how we do that in a minute. And I just realized I've made my slides widescreen and they don't come together anymore. They should all be one stack, not displaced. Apologies. That layer in the middle. Okay, so we've been working with structures like this for many years. This is just some examples of our work from the last year or so. Putting a solid material between two graphene sheets means that you can look at something in an electron microscope that would otherwise be really sensitive to air degradation. So you exfoliate a crystal that's air sensitive in a vacuum or a glove box environment. You encapsulate it between graphene. The graphene prevents the air from getting at your crystal, and then you have all the time in the world to take it to the electron microscope and do your imaging. And this is some examples here for some air-sensitive crystals, chromium tribromide, and this one was tantalum disulfide, which was oxygen uptake. And strangely, when you add oxygen to tantalum disulfide, normally oxidizing stuff makes it worse. In this case, it improves the superconductivity. However, this isn't liquid. You'd expect solids to stick together. So there are two big groups in Manchester, particularly that led by Andre Geim, who over the last 5 years has been really interested in understanding how liquids flow through confined channels, liquids and gases. Why is he interested in that? We mentioned earlier this understanding of fluids in nanoscale environments is important for batteries, it's important for fuel cells, important for understanding how membranes perform. It's also really important in lots of biological systems. The water in your bodies is flowing through gaps in proteins that are of the order of a nanometer or so in size, but studying that is really challenging. The reason that studying that is really challenging is because most of the experiments are done using lab on a chip type devices which are made from silicon nitride or silicon oxide. And silicon nitride surfaces, when you pattern them or even when you grow them, have a surface roughness of between 1 and 10 nanometers. If you are trying to study the flow of liquid through a nanometer sized pore, when your surface roughness is a nanometer, then your flow is entirely governed by the flow or the interaction with that rough surface. And so two-dimensional materials give you this opportunity for atomically flat surfaces, and this is a picture here of the surface roughness comparison between molybdenum disulfide, which is a two-dimensional material, and silicon nitride, which was the flattest possible silicon nitride we could come across, and then just an amorphous carbon surface, which is the quantifoil. Okay. So the way that they study liquid flow through confined channels is to use these 2D heterostructures. And that's the sort of device that you can see here. The liquid will flow through the gaps that have been defined by patterning the two-dimensional crystal, graphene or whatever else. The scanning electron microscope can show you those channels, and they're typically hundreds of channels, but it's only in the transmission electron microscope that you can see the channels that are really interesting and that can do things that silicon nitride or silicon oxide can't study. And so you need the transmission electron microscope to iterate over many years between those making the devices and those doing the TEM and the fib cross-sectioning to be able to see which channels are full of gunk and which ones aren't, to develop those fabrication protocols so that you can reliably produce channels that are empty and that you can therefore flow liquids and gases through. So this is how you study the flow through one of these graphene capillary devices. You put water in a bucket on the top and wait for it to flow out of the bottom, and then study how much weight is lost. And when they do that, you find, again, big surprises happen when you make the dimensions of the nanoscale. So this is showing a gap which is just a nanometer or so. So that's 3 missing layers of graphene. So 3 layers is about 1 nanometer thick. And you can see that the flow through that 1 nanometer thick channel is a factor of 5 greater than when you have a channel that is 10 nanometers thick. So this unexpectedly fast flow through nanometer sized channels is due to the fact that the water takes up a different configuration when it is in a nanometer sized pore, and that means that you get this structural order which causes an enhancement of the flow behavior. And just to say also, they've studied the flow through gases. So this is a TM image of a cross section, and now this is just 1 atom missing in a molybdenum disulfide nanocapillary device. And what's really interesting here is even the fact that in a molybdenum disulfide, you've got sulfurs, yeah, and the sulfurs stick up. And it turns out that the sulfurs sticking up causes roughness, and the gas molecules that are flying through or flowing through that gap can feel the roughness of the sulfur atoms that are sticking away from the molybdenum disulfide, as opposed to in graphene, where the surfaces are really atomically flat. So molybdenum disulfide actually wasn't the best example of an atomically flat surface. If you're a gas molecule, a graphene surface is significantly more atomically flat, and the significance means that you get a different type of interaction with the surface, and that leads to specular rather than diffuse flat scattering. I guess the take-home message here is that you can flow liquid through surprisingly thin gaps and still get measurable quantities of liquid and gas flowing through these systems. So we wanted to study this, and we came up with this design, which was looking at engineered graphene liquid cells. So we're going to make those little capillary shapes and put them in the electron microscope with graphene above and below, thin graphene layers, and now we can choose how much liquid is going into the environment. So we did take this device, and we can now see our nanometer-sized particles moving around inside the liquid. We get atomic resolution, good resolution elemental mapping here. We're actually getting better resolution elemental mapping than when we don't have the liquid environment. So if we burst the cell, and Alex will tell you that if you leave an electron beam on a sample for too long, you drill a hole. So we can do that to remove the water from our liquid cell. And I'm fortunate I'm the director of the Electron Microscopy Center, so I have to complain to myself when I let water into my electron microscope. But it's femtoliters. You're talking very small volumes, 100 nanometers by a nanometer or so in thickness. But we can now measure the difference in the behavior when you have a dry cell and when you have a cell full of liquid. And I'll tell you more about that in a second. But just in summary at this point, hopefully I have convinced you that when we're trying to do our ideal experiment, which is that fish tank, the conventional liquid cells are really, really powerful, but the presence of that thick liquid cell degrades the resolution. They do have some advantages for doing functional experiments. The graphene cells give us these beautiful atomic resolution images, but they're really hard to work with, and they're quite hard to go beyond an experiment which is done triggered by the electron beam. And then we have our engineered graphene liquid cells, which I'm now going to show you how we can take that and go a little bit further than we could before in the last 5 minutes. Okay. So this is now our graphene liquid cell, and rather than just having 1 pocket of liquid, we've put 2 pockets of liquid, and we've stacked them on top of each other. So we have a pocket of liquid which is full of green atoms and a pocket of liquid that's full of red atoms, and now we can do real chemistry experiments, because we can use the electron beam to burst or to pierce the separation membrane that is between those two pockets of liquid, and that causes those liquids to mix inside the electron microscope. And you can watch then at the atomic scale a picture, a video of two liquids mixing, and that really is the first time that anyone's been able to do that. I'm not going to go into the details of the fabrication. It is something that originally took 3 months and now is, once you've got the layers made, takes a couple of hours. So there's been a huge amount of work trying to develop this to make it happen much more quickly than it used to and much more reliably. We've gone from 1 in 10 working to 9 out of 10 working. Okay, but we are making the liquids mix by using the electron beam to drill a hole. Spontaneously, we have a stress in that middle layer, and so that means we get a crack. So we don't just have to wait for water to flow through that 5 nanometer pore. The cracking means that we get widespread mixing throughout that 100 nanometers or 200 nanometer liquid volume, whatever it was.
Temperature effects associated.
Yes. So there, the interaction of the electron beam with the sample, which was the question, is a really important one, and it can cause probably temperature heating is much less important than the radiolysis effects, the interaction of the electron beam with the liquid, which has a whole lot of effects, including changing the pH. So yes, there's lots of things that need to be considered. So I'm not going to go through the details of this. If anyone's interested, I'm glad to talk through it. This experiment we decided to start with was to study a well-known liquid-liquid mixing reaction, which forms the calcium carbonate. And calcium carbonate is a very complicated reaction. And I think the comment just now about what happens to the effect of pH is a really good one, because absolutely the pH can affect calcium carbonate growth behavior. There's an effect of confinement potentially, and I can mention that later if people are interested. However, there is still a lot of controversy about this process, and it's really important. So it's used in marine organisms, is calcium carbonate. It comes up all over the place as an important industrial material. And cryo-electron microscopy had looked at the structures that had been formed. Conventional liquid cell electron microscopy with the commercial holders had looked at the mixing products but couldn't see the earliest stages of reaction, and it couldn't see them when they were down at the nanoscale. The problem with the commercial mixing cell holders is that their liquids mix outside the region that you're looking at. So what you see is the reaction products that were formed tens of minutes ago. So we decided to have a look at this experiment, and again, in the interest of time, all I wanted to show you is that if you look in these images, you'll see big, bright blobs that are floating past the field of view. And that is the first thing that you observe when you cause this initial crack to happen. You get these blobs of bright liquid. And we can tell that they're liquid because they zip past the field of view very, very quickly. You'll see it in this image. Sorry, that's a 5 nanometer scale bar up there. And this one is a 25 nanometer scale bar. So you can see the liquid, that interference type stuff. That's because liquid is moving. And this got Dennis Gabauer very excited, who understands about calcium carbonate formation, because he says, look, this is the first evidence that you really do have before you get these nanoclusters being formed, which was thought to be the earliest stage of nucleation of calcium carbonate. You have this dense liquid phase that is where the clusters are formed from. And this is evidence of this spinodal decomposition. So we've done lots of analysis, and you don't need to know the details of that. Effectively, to be able to study the full process of calcium carbonate formation, we have to turn off the electron beam and then turn it on again after 10 seconds, after 20 seconds. But the great thing about our liquid cells is that we have many different cells within a single array. So we can repeat that experiment multiple times. So we can crack one cell, and because we've got this perfect hermetic seal between cells, neighboring cells, we can do the reaction in one region, repeat it in a different region, repeat it in a different region. So we can blank the beam and watch what happens after a minute. We can blank it. In fact, that one happened when we went for coffee and came back and thought, oh, oops. So yeah, so you can do the experiment at different time points. Right, so just to finish up, the same type of heterostructure system where you have a liquid above and a liquid below and then a membrane in the middle is what allows us to do atomic resolution imaging. In the previous experiment, there was atoms that could be seen within the layer, but calcium carbonate that's being formed wasn't crystalline. And it's also relatively electron beam sensitive. So we didn't get to see any atoms. And what I really enjoy doing in my job is looking at atoms. And so we wanted a solution that we could look at and investigate atomic behavior in the liquid phase. And so we chose platinum on molybdenum disulfide. So platinum on molybdenum disulfide is really important for the hydrogen evolution reaction. Sorry. And the addition of platinum causes a big enhancement in the performance for the hydrogen evolution reaction of the molybdenum disulfide layer. However, all of the characterization of those materials has been done in the vacuum of the transmission electron microscope. And there was a clear discrepancy between the position of the platinum atoms predicted by density functional theory and the position of the platinum atoms on the molybdenum disulfide surface, which was observed in the transmission electron microscope. So this shows you the liquid cell structure. You can focus using a scanning probe, so you can focus on the different layers. The focus of the top layer is just the graphene with platinum. This is the molybdenum disulfide layer with graphene. This is another graphene layer. Okay, so you can see that it's 70 nanometers thick. And this now compares, sorry, I should turn the lights off. This compares the behavior of platinum atoms moving around on the molybdenum disulfide surface in the sorry. Just look at atoms for a minute. I'll show that again because I think it's beautiful. Okay, please, gonna start again? Maybe not. Yeah, okay. So you can see that, well, maybe you can't with this projector. There is a better signal to noise ratio in the vacuum images. But even in the liquid cell, you can see the molybdenum atoms within the substrate, and you can clearly see the individual platinum atoms, those bright dots, individual platinum adatoms on the surface. When the platinum is absorbed into the liquid, it disappears. Ions in solution move orders of magnitude more quickly than we can possibly image using this imaging mode in the electron microscope. But we are able to see the adatoms moving around and to quantify their motion. We can see where they're sat. So this shows you the position of those atoms relative to the underlying lattice. And if we combine those measurements, and we're measuring 90,000 different atomic locations, you can build up a histogram to be able to look and compare the expected or the most common positions for platinum relative to the underlying molybdenum disulfide surface. And all you need to take home from the message of this rather complicated diagram is that in the vacuum experiment, the platinum is almost always above a sulfur atom. And that's because in the vacuum environment, the vacuum creates sulfur vacancies together with the electron beam, and just one image is enough to create sulfur vacancies. Those sulfur vacancies stick the platinum into the surface, and you end up seeing platinum jumping from sulfur vacancy to sulfur vacancy and not really seeing what you would get when you don't have those sulfur vacancies. The presence of the liquid compensates for those sulfur vacancies, and now you can see the platinum sitting both above the molybdenum and above the sulfur locations and hopping between the sites. We've done this experiment by taking a molybdenum disulfide layer, just putting platinum solution on the surface, drying it out, putting it in vacuum. We've also done the same experiment by drying out our liquid cells. So these is an example of the tracking that Nick does for a data set. You can see we've got the tracking of the positions in the molybdenum disulfide layer, and then you can look at how the adatoms on the surface are combining to produce nanoparticles and moving around. The important message is that in the liquid environment, as I guess you'd expect, the motion of the platinum atoms is much more faster, it's much quicker. Yeah, the mean squared displacement is much higher when you have a platinum moving on a molybdenum disulfide surface in a liquid environment. Question about the electron beam. The difference between dry vacuum and liquid is much greater than the difference between the amount of electron beam we're putting on our sample. So we've done the experiments with different electron beam dose per second, and we have found that there's a bigger difference between the behavior of the material in liquid and vacuum compared to the effect of the electron dose. Interestingly, and again, you don't have to get the details of this, it's surprising that if you use the lowest possible dose to still be able to see the atoms, then that's when you get the fastest motion. And that's kind of surprising, since you'd think the electron beam was giving the material the energy to drive the motion of the atoms on the surface, atoms. And so the explanation for this is not clear, but perhaps it's because the electron beam is also creating ions on the surface that are also able to interact and slow down the surface. So you end up with a sweet spot where you've got enough energy from the electron beam to encourage the platinum to move, and you're not creating so many defects to pin. But this is still very much an area for ongoing investigation. Lots more things that we should be able to learn. Okay, so in conclusion, I hope that I've shown you that a 2D heterostructure liquid cell approach has some advantages if you want to be able to look at chemical reactions. There's still an awful lot we don't understand about the interaction of the electron beam with the liquid and with the solid, but it is now giving us the first opportunities to be able to study at the atomic scale solid-liquid interfaces and also the behavior of liquid-liquid mixing reactions. This paper on the bottom, I haven't talked about, but the development of this technology was done in the group of Roman Gorbachev, and really was, 5, 6, 7 years of work, and is now at the point where we can concentrate on doing the science and concentrate less on making the samples, because this has now become a reliable fabrication approach. So in conclusion, I'd like to thank very much all of my research group, particularly Nick Clark, who's led the liquid cell group, and Yichao Zhu, who's now moved to an academic job in China, who led the clay work. And of course, I'd like to thank the funders and you for listening. Thank you very much indeed.
Thank you so much for the impressive presentation. So the floor is open for questions. Yeah, Joao, please.
Thank you, sir. I had a question on the, I guess the double-edged swords of looking at very small scales versus, I guess, a statistical representation of phenomena. And so I was thinking, often in scattering, we think of that as being a kind of a compromise that we make. We look at large sample volumes or areas, and we do that in reciprocal space, so we pay that price. But at least we sample, many moles, so to speak, of molecules that can then therefore allow us to do some statistics. And it struck me that in this case you get immense local resolution, but also presumably also will be affected by the stochastic variability, right? So is that really, that one chemical reaction that happened in that specific way, how representative is that? And other than repeating that, 10,000 times, how do we make sure that we sort of take the benefits from both?
So it's a great question, and it's a question with all electron microscopy. Yeah, the amount of material anyone's looked at in an electron microscope is for the whole of since electron microscopy was invented in a TEM is this much. We are developing a lot of machine learning techniques which now allow us to take data sets that are enormous. And so the histograms that I mentioned there are an average of 90,000 atomic positions. So that's still small compared to X-ray analysis, but that is a very large number of atoms compared to what people normally study for size analysis of a nanoparticle, where you measure 10 particles and say it's 10 nanometers or whatever it is. So I think that a lot of the automation that is happening in electron microscopy now is helping us to be more like the cryo-electron microscopy community, where they automatically analyze the whole sample and then they average the data from 1 million proteins to be able to give you one crystal structure. Actually, the platinum nickel particle I showed you at the beginning is an average of 600 nanoparticles. And what is clever about that is you can then break it down. So if you've got that resolution for 600 particles or 90,000 atoms, you can then separate out and look at, okay, what about the first 10,000 compared to the last 10,000 atoms? And that's what we've done to see that those atomic locations are robust to pH, because there's no difference from the first set of 10 images compared to the last set of 10 images. The liquid cells are great because when the reviewers' comments came back, we put the same liquid cell back in the microscope and it was still containing liquid and behaving the same 12 months later. And that is definitely not true of the original graphene cells. So I think it's twofold. It's about helping electron microscopists to get more and more data and also be able to analyze that data quantitatively in a computer rather than by eye. And also building up the automated electron microscopy so that we can pick up those large data sets in a more intelligent manner. And I think there is big progress in that direction. Makes sense. Yeah, hi.
Wait for the microphone, please. Yeah.
Thanks, Sarah.
It's on. It's on.
Hi. That's a wonderful talk. So I'm wondering, because you mentioned you have done a lot of liquid cells, but most of your work presented here are done in water. So what about the organic solvents? Because that could be really interesting, because you mentioned about battery applications or membrane separations, because membranes could also be used for separation of solvents or in the solvent medias. You could also maybe perform some reactions in the solvent media, like you look at the nucleation or crystallization. So that might be really interesting.
That's a brilliant question, and I didn't plant you in the audience, I promise. To start with, when we were doing these experiments, we could only look at water because the final graphene layer is transferred stuck onto a polymer layer. And that means that if you have a solvent that would dissolve the polymer, and many of the solvents we were interested in would dissolve a PMMA layer, then we weren't able to put anything that was organic into the liquid cell. We've now overcome that. We've got a new way of making the liquid cells, which means that you can use a wide range of organic solvents. So we've done hexane, acetone, lots of different organic solvents now, which I agree offers a much more potential for the sort of experiments that you might want to investigate. The only caveat to that is that the understanding of radiolysis in organic solvents is less well developed. People understand radiolysis in water to a certain level. It's even less well understood. And our experience is that they change more quickly under electron beam dose than the water solutions, which seem to be surprisingly robust. I think it's probably more surprising that the water is so robust than that the organic solvents aren't. But definitely we can have a chat, and that was a limitation. It's not anymore.
Very much. Another question here, please, with Magda.
I'll try and be short.
Actually stole my question, so I was gonna start, but then just to follow up, clearly electrification is the future, so can you stick a potentiostat at any point to look at how atoms change in real time?
So we have done experiments without liquid, looking at applying a bias potential and changing, causing intercalation, for example. It's work in progress, yes, to make it happen with liquids. It's more challenging, but it's absolutely possible.
Even with water for the start. That'd be brilliant.
Great.
Okay. Thank you very much. Any other questions from the audience? I was wondering regarding the graphene you use, is it always CVD graphene or could it be prepared with other types of graphene?
So it's never CVD graphene.
Not even CVD.
It's always HOPG, highly orientated pyrolytic graphite, because the group, which is Roman Gorbachev's group, have used HOPG to produce the most perfect transistor experiments. There isn't any reason why you shouldn't be able to use CVD graphene. You don't want monolayer, you want bilayer, but again, that's relatively achievable. Achieving the right thickness of the spacer layer, so that one that you pattern to make the right size of pockets, that's a bit more hard to reproduce with CVD materials, but is definitely something that we'd like to be able to do to help give that to more people, make it more accessible as an approach. But yeah, so great question. But no, it's all sticky tape and pencils because we're in Manchester.
Thank you very much. So There's nothing online, so yeah. So we will close it here. Thank you very much for your presentation, and a big applause to you. Thank you.
Thank you.